All right, so my session is going to be about pure pursuit for autonomous navigation. So my name is Anthony Wang. I've been in FIRST for 10 years. This is a history of which FIRST programs I've been in. I'm the software leader in our team. I enjoy skiing, tennis, and CSGO. All right, so here's today's agenda. So first, we're going to go over the basics of autonomous and why we need complex algorithms. And then we're going to talk about these algorithms like pure pursuit and Roadrunner. And then we're going to go over the debug client, which is how we simulate autonomous paths for tuning. And then we have a case study where we compare pure pursuit and Roadrunner. And then at the end, we'll have conclusions and future improvements. All right, so most teams in FTC start off with basic functions such as like turning and go forward and backwards. And with these functions, you could go anywhere on the field, but often they don't really correct for errors. So like these errors will end up accumulating if you turn a little bit too much, you're gonna be like completely off by the end. So basically we need complex algorithms because they can correct for this. Complex algorithms, they also can allow you to curve and avoid obstacles. And you can also turn while moving forward, which saves time. All right, so here are the basics of pure pursuit and Roadrunner. So Roadrunner, it computes a point in a velocity vector as a function of time. So basically, at every point in time, the robot tries to get as close as possible to this point in velocity vector. And it adjusts itself using a PID controller to try to achieve the position and velocity. And pure pursuit, the path is defined by connected line segments, and the robot tries to pursue a point. And that point is defined by the intersection of a circle and one of the line segments. All right, so let's compare pure pursuit and Roadrunner. So pure pursuit is location-based and it's not time-based. So it's basically going to keep, if you let it stay in one place, it's going to keep doing the same action until it moves. But Roadrunner, it's time-based, and it only tries to correct for errors, like errors off its predicted position. And pure pursuit, it's really difficult to make sharp turns, but Roadrunner, it features like turning capabilities. Pure pursuit, the algorithm's easy to modify, but Roadrunner is like in a packaged library, so it's kind of hard to modify the algorithm, and it's like a lot more complex, and it's also written in Kotlin. Let's see, pure pursuit is generally faster because you're directly setting the motor powers to a maximum possible speed. And Roadrunner, it can go fast, but it has to be tuned very carefully in order to do so. Pure pursuit, it's not very accurate. It won't necessarily end at the designated endpoint, and the robot can go anywhere within a certain radius of the path. But Roadrunner, it's pretty precise within about like an inch or a few inches accuracy for every path point. All right, so here are the key points of pure pursuit. So in the pure pursuit algorithm, we have like a path defined by connected line segments. So the algorithm looks through every single line segment in the path, and then it checks, is there an intersection between this specific line segment and a circle around my robot? And it looks for an intersection and then tries to follow that intersection. And the robot prioritizes points closer to the end. In our implementation, it only checks for intersections for each line up to a certain path point. It only extends the path while it touches the last available point. So here's an example. So basically what we have on the very left, that's our entire path. This is an example path. But basically in our implementation, we first give it this path, and then we only extend the path once the robot reaches the end of this path. So the robot reaches the end of this path, you give it another line segment. The robot reaches the end of that path, you give another, and then so on. And so the reason we do this is because otherwise the robot would immediately jump from like the first line segment to the last line segment. So this way you can like repeatedly visit multiple points. That just makes the algorithm better. And also we extend the ending line segment because the way Pure Pursuit works, it's like your robot is defined by a circle with a radius. So you just extend the last line segment by that radius, so the robot has an intersection point to follow at the very end. All right, now we're going to go over the debug client. So basically the debug client, it just renders points. And so basically there's this whole framework that allows you to simulate the physics of your robot, and the debug client just renders it. So basically, here's a diagram. In our team code repo, like our main repository, we have our Pure Pursuit algorithm, and then the Pure Pursuit algorithm, it communicates with the physics simulator. It communicates velocity for like X movement, Y movement, and heading movement. And then the physics simulator takes in that and uses that as acceleration, and like it calculates your robot moving and friction and all that stuff. So your Pure Pursuit code is shared by the physics simulator and the real robot. And then the physics simulator itself communicates with the debug client. So it sends like packets. I'll show you the code in a second. It sends packets to the debug client, which is like you run the debug client. It's an application. It's a Java application. All the debug client is like renders dots that you send to it, and lines and circles, whatever you need. All right. So here's an example of the code in the debug client. Well, no, this is actually code from the simulator. So it builds a message. It's in this format, and then it sends. They connect to each other using a UDP server. And then here's the physics simulator. So it takes in movement X, movement Y, and movement turn, which serve as acceleration and X, Y, and rotation. The simulator also simulates friction. So at the top here, it's like incrementing your roll position based on your velocity. And then here is changing your speed based on your essentially simulated motor powers. And then at the bottom is where it calculates friction. All right, so I'll show you a sample of the simulator. The video isn't working. There we go. So Pure Pursuit follows the path like that. And as you can see with our implementation, we can revisit points. So yeah, the simulator, and then here's the simulator in sync with our real life robot. So what you're about to see is the simulator. I'm running it by itself, and then the robot is running the same Pure Pursuit code. So these both have the same code. It's just one of them is running with simulated physics, and one of them is running with real physics. So as you can see, like the simulator in real life matches up pretty closely. Wait. I'm trying to look at chat. Hold on. Oh wait, what? All right. All right, so basically that video just showed that the simulator matches up to real life pretty well, and you can also tune the simulator to be even more accurate with your specific robot design. Okay, so, and then next we have a case study of pulling the foundation. So basically, by this point, I kind of concluded that both algorithms, like they both have benefits or like over each other, so we need something else to test the algorithm with. And since we struggled with pulling the foundation in the season, we decided to use this pulling the foundation to test our algorithms. And so basically, we just want to see time-based versus position-based. And we also chose this case because it requires a large torque. So here's Roadrunner pulling the foundation. All right, so as you can see, it pulled it with relative ease. And like it pulled it with a smooth curve because Roadrunner like naturally works with the splines. So near like the turning part of the video, it's turning while moving. There's a ton of benefits. And then here's the Pure Pursuit video. All right, so as you can see in the Pure Pursuit video, it wobbles a bit because that's just the way the Pure Pursuit algorithm works with defined line segments. And so that's one of the problems with Pure Pursuit. It just can't follow curved paths if you give it a situation like this, and it ends up making that wobble, which slows it down. So let's go to the conclusion. So mostly, it's going to depend on the game. Which algorithm you're going to use is going to depend on the game and the situation. So like, yeah, you can also combine Roadrunner and Pure Pursuit, as in like, you can use Pure Pursuit for one part of your path and then Roadrunner for another part of your path. It's completely possible. But in general, Pure Pursuit is suited for accuracy within like a 1 or 2 inch margin or more. So you're not going to be extremely accurate at the end, but Pure Pursuit is very easy to max out the top speed of your robot. So like, because Pure Pursuit has constant acceleration, you can just set that acceleration to the max, and it's easy to like get the max speed of your robot. And Roadrunner, it's possible to make curved paths easily, and that makes certain actions easier, as you saw in the video. But with Roadrunner, it's pretty hard to achieve max speed because you have like 10 constants you have to tune, and it's like a total pain to tune Roadrunner to achieve max speed. But Pure Pursuit, it's easy. So basically, Pure Pursuit is faster but less accurate, and Roadrunner is slower but more accurate. Okay, some future improvements is to have Pure Pursuit to have better ending accuracy, because right now we just like cut the motors at some arbitrary point and hope the robot ends up at the ending point. So yeah, that's a problem with Pure Pursuit. And also get Pure Pursuit to follow Roadrunner paths, because Pure Pursuit is made up of line segments. We can possibly have Pure Pursuit to like interpolate the splines from Roadrunner, and if Pure Pursuit follow those. All right. And credits, thanks to Gluten Free for the debug client and the simulator. They developed that, and they also provided the basic algorithm for they also provide the basic Pure Pursuit algorithm, which we built off of. All right, any questions? Let's see. All right, if no one has any questions, I'll stop sharing.
Oh wow, okay.
We can move on to our next presenter, which is Byron.
Yeah, so I'm just gonna start sharing my screen and share my slides. So today we're gonna be talking about guiding vector fields for autonomous navigation. So we just heard Anthony talk about like Pure Pursuit a little. Guiding vector fields, or GVF, is basically another path planning algorithm like Pure Pursuit, and Anthony talked about Roadrunner a little bit. So yeah, so real quick, we're gonna go over my bio. I'm Byron. I'm a rising sophomore. I go to Jasper. I joined 8565 just last year, and I'm a programmer. And in my spare time, I like to read books. It's not on here, but I also do debate. And yeah. So let's go over a quick list of topics for today. So first, we're going to touch on goals on autonomous and explain why we even need all this stuff. Then we're going to go on to the Roadrunner library, and then we're going to talk about guiding vector fields a bit. We're going to talk about how we implemented GVF. We're going to talk about GVF versus traditional Roadrunner, and then we're going to wrap it up. So let's start off. Basic concepts. Yeah, so autonomous. I think everyone here knows what autonomous is. 30-second period, predetermined program, and it's really important because you need to score a lot of points here. So auto programs have to do two main things. They have to be efficient, so they have to score a lot of points, and they have to do that consistently. So they have to score this every round. So for these purposes, path planning algorithm is very useful because it makes your path more efficient and you can get to more places and also more consistent because you can correct mistakes and drive more accurately. So that's why we need stuff like Roadrunner. Roadrunner is a motion planning library designed for FTC that allows us to accomplish this pathfinding. Last season, we used Roadrunner for our autonomous. These work through paths. They're basically a series of points that a robot is expected to go through. So as Anthony explained, these paths, you basically signify 2 points on the field, and then Roadrunner automatically connects them together with a curve or spline. So you feed, but all that's done by the library. You don't have to worry about much of that by yourself. You feed the robot's location. You get that through odometry wheels usually, through a function to determine the wheel powers, and then the robot just drives to your location. So this works through trajectory, so which is time and location based. So a robot, it determines a motion profile. So you determine exactly where you want to be on the motion and acceleration at every point, and then you just follow it. And then we put constraints onto acceleration and velocity for consistency and greater control. So guiding vector fields. So besides the standard pathfinding, so what I just talked about, Roadrunner also has a guiding vector field path follower using the algorithm described in a research paper. So that's linked in the credits if you want to read that. But basically in GVF, paths are based on location alone. So unlike a normal Roadrunner where there's different times and a motion profile, and GVF, if you're at a certain point, you'll always have the exact same target velocity and acceleration. It's not dependent on time at all. Yeah, but these also include motion profiles to limit acceleration and velocity. So this is kind of a visualization of what it actually means, like guiding a vector field. So the vectors are these little arrows, and if a robot starts here and you want to follow this dotted line for a path, you basically follow the direction of all these arrows, and then as you can see, the arrows will lead you towards following this path. So it's exactly as the name says, it's a guiding vector field. So how do we implement all this? So we do this through followers. So as we already talked about, a Roadrunner path is a series of points, and then you draw a spline or a straight line between them. However, once these points are defined, you still need to follow them. So in other words, you need something to convert your current location of the robot to what your robot wants to do. So Roadrunner has several such path followers for this. Default, what we talked about, this is what we used last season, the holonomic PID follower. And for GVF, we use another one just called the GVF follower. They both work in the same way. You get the robot location, and then you spit out the target speed and velocity, and then you feed that into your motor powers. So implementing GVF, you just have to switch out the follower class in kind of the middle, but the method of getting location and your overarching robot class remains the same. So you don't have to rewrite your entire thing. So this is kind of a flowchart to help you visualize the GVF algorithm. So you specify your path, then either you generate your GVF, your guiding vector field, or you generate your motion profile, and then you get your robot location from the odometry wheels. Then you feed that into the algorithm. It gives you your velocity or your acceleration. Then you feed that into your robot class. Our class is mechanism drive because we use mechanism wheels. And then that gives you your motor powers. And then we just feed that to the control hub that drives the motors, and it gets the robot to move. So this is just some code snippets. Roadrunner, you path build. So you create different line to or spline to's like coordinate points, and then you define a follower. You set the follower to follow this path, your path, and then in your loop, you update your follower with your current location, and then that gives you a drive signal, that's basically like the list of all your target motor powers, and then you set it to your drive, and the robot moves. So while we were testing this out and implementation, I also used a debug client Anthony was talking about. So Anthony already explained much of how this works, the physics simulator and the debug client itself. So I'm not going to go into too much detail. But yeah, the implementation is a little different with Roadrunner. But the end result is the same, in which you're completely simulating. So you don't need a robot at all. You just simulate your path and see what the algorithm is going to do. And this is it's almost essential in this season because obviously with the entire pandemic, we can't go to meetings as often. We can't work on the actual robot, so we have to do a lot of our work at home, and this is really helpful. Yeah. So testing. So after we have all the implementation done, all we need to do is test the GVF and see how it works. So what we did, so basically, as I described in the implementation, we just switch out the follower, but keep our old auto path that we already tuned, and test the path several times to see how GVF compares to Roadrunner. So while testing, we found that GVF, or at least this implementation of GVF, has a big problem. So when you're trying to go in straight lines, the robot turns instead of strafing with mechanism wheels. I'll show you guys a diagram later so you can visualize it better. But yeah, it seems to not recognize the mechanism chassis, and it's instead behaving like a tank drive. So the path we're using no longer works because it's designed with strafing in mind. So with this limitation in mind, we didn't have enough time to rewrite our entire path with GVF. So instead, we did some pure speed testing. So we just timed a simulated path without stones or foundation, so we can just compare the two algorithms' speed without having to worry about strafing or turning. Yeah, so this is an algorithm comparison. GVF we found actually does have more speed, especially when you're turning in place. However, as I talked about, you do have to move before you turn in the line, so that causes inefficient pathing. So yeah, in Roadrunner, you can strafe with your mechanism chassis, so it's more efficient. So if you have your robot here on Roadrunner, you can just move directly over here without changing your heading at all. But in GVF, if you start in the same location as this Roadrunner robot, GVF makes you turn first and then drive in a straight line to over here. And then you're not in the same angle in which you started off. So that might cause problems in your auto. For example, our robot, we have a side claw over here that's supposed to pick up the Skystones from over here. But if GVF turns, then the side claw is misaligned and it's not in a proper position to pick up your stones. So instead, we recorded some videos. These are videos of the speed testing I just talked about. So just to give you an idea of how the two algorithms work. So just slow the stack down to normal speed and God. All right. So as you can see, GVF, you have to turn before you drive in a straight line. And then here, instead of just directly moving backwards, it turns around and then it heads backwards. So that causes a bit of inefficient pathing. But if you look at Roadrunner, just set this down to normal speed again. And if you look at Roadrunner, it has the capability to strafe. So yeah, and it moves backwards as well. However, you might notice that this video is 10 seconds long and this video is 8 seconds long. And if you compare it side by side, you can actually see that GVF is moving, and especially here, turning a lot faster than Roadrunner is. So there definitely are some advantages to using GVF over Roadrunner. So conclusions. GVF certainly has a lot of potential. Yeah, it can be much faster than traditional Roadrunner, useful for completing more tasks, it turns faster, and in general, it just moves a bit faster. However, when you implement GVF through the Roadrunner library, it's meant for non-holonomic or aka tank drives, which means that the mechanism drives we use aren't used to their full potential. So future study can be done in the GVF algorithm for holonomic robots, which are mentioned in the paper. So yeah, Roadrunner does have a fork with a more advanced GVF algorithm with support for holonomic drives. We only just found this out like last week, so we weren't able to test this out, but it does exist and it's something to look into for future research. Yeah. And finally, we have our credits. So Roadrunner, the entire library was developed by FTC Team 8367, Acme Robotics. This is their site. They also developed, I think, FTC dashboard, so they made a lot of really useful stuff. And these three people were the authors of the GVF algorithm, and that's basically where Roadrunner got the entire GVF algorithm. So they wrote this paper, so you can check it out if you're interested. And the debug client that I talked about was developed by Gluten-Free 11115. So this is their YouTube channel here. And that's about it. Anybody have any questions? Chat.
If not, then we can move on to our second to last presentation from Hrithik.
Yep. Yeah. And if you have any questions for any of the presenters, you can just ask later on, and then we'll get to it when we have time.
Mm-hmm.
I'm going to cover over one-button automation Teleop, also known as OBA. Before we get more into it, I'm going to share my presenter bio. Hi, I'm Hrithik Maniyambeth. I'm a ninth grader at Frisco High School, and I've had 3 years in FIRST, 2 years in FTC, and 1 year in FLL. And I'm a software programmer. Some of my hobbies are reading books, listening to music, and playing violin and piano. So our agenda for this is going over what one-button automation is, what automation in Teleop is, Teleop with automation versus manual control, and the main challenge for one-button automation. Our case study is, in simple words, making the robot score 1 stone by pressing 1 button on a gamepad. And then I'm going to go over some problems and issues I've had. They're like really small problems I've had. And then I'm going to go over the conclusions. So before we can dive right into it, we have to know what automation in Teleop is. So drivers are under tremendous pressure during matches to score as much as possible. And the main job of a Teleop programmer is to make the driver's life easier by using simpler button control, using sensors to automate controls, and using LED to provide feedback to the driver. For example, last year we had the LEDs on the bottom of our robot turn specific colors when like the claw clamps onto the stone, when it goes into slow mode, and when we retract the lift system back. So in some past automation developed by our team, which have been adapted successfully in our competition matches, are detecting the number of minerals in a robot cargo system by using 2 distance sensors, and then automatically resetting the lift system to its initial state after scoring. The main reason why we have this is so that it reduces the amount of work the driver has to put in, and it also reduces the time from scoring 1 stone to going back and getting another one. And then the next one was automatically clamping the stone once we take it in by using a touch sensor. And the main reason for this is because the driver can't really see the clamp and claw in the middle of the robot. So it makes it kind of easier for the driver not having to worry about clamping the stone and unclamping it every time they get a stone. So now here's a small table of the differences between automation, Teleop with automation versus Teleop with manual controls. Teleop with automation has simpler gamepad control, and it may use while manual control may use up all buttons on the gamepad. And this has a heavy cognitive load on the drivers, meaning that the driver has to think about what each button does, when to use it, and how to use it properly. Teleop with automation has more accurate information collected by the sensors, assuming that the robot and the sensors have a good design, while Teleop with manual controls, the driver may not be able to view all angles up and or up close due to the fixed driver station at the competition field. An example of this is when we were aligning to the foundation. It's kind of hard for the driver to see if the robot's aligned to the foundation properly because the driver can only see it from one specific angle. Teleop with automation relies on good strategy design and consistency of the deployed sensors, while manual control relies on driver training. So for automation, there are some like complicated automation scenarios, and for that, extensive testing is required to boost the confidence of the driver team for adaptation. While Teleop with manual controls, the driver can move the robot smoothly with enough practice, while automation takes a lot of testing to make the automation viable. So our main question for this summer was to see if we can do more, can we do more automation in Teleop? Already in last season, the Skystone season, our team has developed the following 4 automation segments. Align the robot to the foundation using the 2 distance sensors, align the robot to the tower using the second camera, auto scoring the stone on the tower, and auto retracting the lift system and claw after scoring the stone. So based on these 4,
most of the people are in like the other session.
Based on these 4 automation segments, we decided for our case study this summer was to make one button completely automate the robot from when it's getting closer to the foundation with the intake stone to finishing scoring and reset, getting ready to intake the next stone on the field. But our main challenge for this was that Teleop is an iterative op mode where the programmer programs the logic in a loop method, which is called by the FTC SDK at roughly 100 milliseconds, roughly 100 milliseconds interval. Like every 100 milliseconds, it calls the logic in the loop method. So between the actions of the automation, the method has been called way too many times. So for this, we needed a state machine to maintain the sequence. So the robot starts in state 1 and stays in state 1 until event 1 happens that kind of causes it to go from state 1 to state 2. And then a outside event, not outside event, and event 2 happens and it goes to state 3. And it keeps on doing this until it goes back to state 1, which is the initial state, where it can go over the whole thing again. So our case study, the one button automation scenario was at the pressing of one button, we would complete the following from like the initial state. So step 1, we would align the robot to the foundation using the distance sensors, and then it would go into the step 1 done state. Step 2, it would align the robot to the stone tower using the second webcam, and then it would go into the step 2 done state. And then step 3, it would score the stone onto the tower, going into the step 3 done state. And then step 4, it would retract the whole lift system, going into the initial state, which allows it to go through the whole thing again in case we need to score another stone. So for step 1, we used 2 distance sensors, and the main starting state was the initial state, and the triggering event that caused step 1 was a key press. I think it was the left I think it was like a left button or something like that. And the ending state was the step 1 done state. The main control algorithm for this was that the robot compares the two values of the distance sensors and keeps turning until the distance sensors have almost the same value. And for this, we use the PID controller for accurate control. As you can see here on this image, we put the distance sensors like at the bottom of the robot so that I can sense the border of the foundation. And over here is a webcam, which is used for step 2, which was, as I said before, we used a second webcam to align the robot to a stone tower. The starting state was the step 1 done state. The triggering event was when the two distance sensors have almost the same value, which means basically when the robot's done aligning with the foundation. And then the ending state was a step 2 done state. So our main control algorithm for this was using OpenCV to put like a yellow filter on the image to figure out whether the tower, where the tower was to align with it. We used pixels. Using the pixels, the robot figures out whether the stone tower is left or right and moves horizontally until the tower is aligned in the middle. And we use a PID controller for this. So basically what it did was it kind of blacked out everything that wasn't yellow and highlighted everything that was yellow. As you can see in this image, it blacked out the whole background, but it only highlighted the stone tower because it was yellow. So step 3, we used a lift system motor encoders, and the starting state was a step 2 done state, and the triggering event was the left edge of the tower reaching a targeted position, meaning that the robot was aligned to the tower, and then the end state was step 3, the done state. The control algorithm for this was, since we can't use sleep in Teleop, we decided to use an elapsed timer to estimate the ending of each of the substeps below, which was grabbing the stone with the claw, lifting the stone using our vertical lift system, extending the stone using our horizontal slides, and then dropping the stone onto the brick tower. Finally, step 4, the last step. For this, we used a limit switch on the horizontal extension system and the lift system motor encoder. And the starting state was a step 3 done state, and the main triggering event for this was the end of the last elapsed timer, meaning that the stone has dropped onto the tower. And the ending state after this whole step is done is the initial state, allowing it to go through the whole process again if we want to score another stone. And the main control algorithm for this was retracting the whole horizontal extension system until the limit switch detects that it's fully retracted. And then after that, it lowers the lift system to the bottom level based on its encoder values. So as you can see here, here's a quick demonstration video. So next, I'm going to go over some small problems and issues I've had with the programming it. So the first one was the usage of the second webcam. This is like a really small problem I had. I tried changing the webcam that the tower alignment function uses. However, when I changed like the webcam name in the code, it still wouldn't use the second webcam. And the solution for this was I had to insert a missing line from the code that uses the parameter from the Vuforia localizer and assigns it to the webcam name. As you can see here, here's the missing line that I forgot to insert in. And basically what it takes the webcam name and actually like assigns it to the camera name. Otherwise, this really didn't have any use in the code. So yeah. So then the next problem I came across was the alignment PID tuning. The main problem was when I first started running the align to foundation function, the robot would shake aggressively, causing the robot to hit the foundation. And the solution for this was I had to tune the PID values using multiple iterations. This took a lot of fine tuning, but ultimately it ended up working fine. I also decreased the time limit on the alignment so it doesn't keep turning for too long. And I mainly decreased the P and I values so that it makes less major movements. So now on to our conclusion. A complicated one-button automation like the one presented in this case study is doable, but the main question is if it can be used reliably in competition matches. And it's probably not. It mainly depends on too many things on the robot, and it requires extensive testing to beat human-trained drivers. So the bottom line for this is that Teleop automation is a picking game. You have to find the right automation strategy that your team can achieve reliably to make it benefit the driver team. So on to the credits. For this project, I only used FTC dashboard to test and tune and also get the image from the webcam. And I think Acme Robotics made this, so thanks to them. And if you have any questions, you can unmute and ask.
Okay, thank you, Hrithik. So before we move on to, let's see. So before we move on to our very last presentation, just a few reminders. First, I still see a lot of you guys don't have your team number next to your name. Make sure you put that there because we are going to be doing the drawing very soon. And secondly, make sure you do fill out the survey, the link I put in the chat. Entering does give you one entry into our drawing for used monitors at the end of the day. If you do win the drawing and receive a used monitor, we will send you an email notification, so keep an eye out for that. So I believe we can move on to our last one, which is Max.
Okay, can you guys all see my screen fine?
Yeah, it's good.
Okay. So for this last presentation, I'm going to be talking about the Blender exploration and bill of materials in Fusion 360. So just a little bit about myself. I am a 10th grader at Lebanon Trail High School, and I was in 3 years in junior FLL, 3 years in FLL, and my 3rd year in FTC. And the hobbies I have are reading, gaming, and playing tennis. So in this presentation, as I said before, we're going to be looking into how Blender works and how to create a bill of materials in Fusion 360. So what is Blender? Blender is an animating or 3D modeling software that's similar to some other softwares you might have used, such as Maya, and we're going to be talking about the Blender basics, how to 3D model, and animating in Blender. So to go more in depth into what is Blender, Blender is a free and open source 3D software that is used for making animations, rendering visual effects, creating 3D models, or many other things. Reasons why Blender is good is that it's really useful for modeling. It can provide really smooth and lifelike renders and animations, and it's good for really large projects. So just some Blender basics to go through. Just in any 3D modeling software, you have to learn how to use the camera movement, how to create objects, how to move objects, and then the different modes. So in Blender, camera movement, of course, there are different keybinds, but by default, it should just be the middle mouse button to move. And for object creation, there is a tab in Blender that allows you to create objects just like in Fusion 360 or in Autodesk or any other 3D modeling software. And same thing for object movement. There's an option in Blender that allows you to move objects, scale them, and rotate them. I believe the shortcut key by default is G for move, S for scaling, and then R for rotate. And then there are different modes. The ones that I used were object and edit mode. Edit mode is just kind of self-explanatory. That's when you're editing it, like you're extruding it, adding extensions to a 3D model. And object mode is just to see the whole model as a whole and just look at the different parts of it. So as I said, there were different modes in Blender, and in the edit mode, this is how you would edit your model. So there are 3 ways to do it. You can extrude your vertices, your edges, or your faces. And I pulled up pictures here, so you can see that there's an option for extrude vertices, extrude the edges, and extrude the faces. And editing in Blender is a little bit different than in editing in Fusion 360 or some of the other well-known ones. The reason is because usually in 3D modeling software, you don't edit the vertices or edges, you just edit the faces. But for this, you can edit objects by selecting vertices or edges and dragging them out to extend them. For example, if I was extruding vertices, I could select all the vertices on a plane or face and drag them out to add an extension to my 3D model. Now for animation. So unlike Fusion 360, in Blender, you would use something called keyframes to save the movement of the objects. And to do this, you would save the keyframes of the location, the rotation, and the scaling. Keyframes basically just save the location, rotation, and scaling of that model at whatever point. So for example, if I had a cube at frame 0 and then I moved it 10 units to the right at frame 10, I could then keyframe it at frame 10 to save the location, and that would and then when I play the animation, it would just perform the action. Another thing for animation, you can also add textures and shaders. This is something that's, I guess, better to do in Blender than some other softwares. I know in Fusion 360 you can also do it, but it's really generic in Fusion 360 and you can't do a lot with it. And in a little bit, you'll be able to see what I mean by that. So here is a sample animation of cube running. This is the first one that I tried. And you can see that I made it first go forward, rotate back, and then scale up forward again. So when animating the robot, I had a little bit of trouble because usually when you animate something, when you're rotating an object, you would rotate it around the origin. But in this case, the origin was not in the center of the robot, and it was actually really hard. So you can see this orange dot is actually the origin point for all of the parts of this side claw that we had. And that was really troubling because if I wanted to rotate the claw, it would move the entire thing around this orange dot instead of around the servo like we wanted to. I tried a couple solutions to move the origin, but unfortunately none of them worked. So I had to animate the hard way by manually, like almost frame by frame, moving the side claw slowly so that it would look like it was realistic. So this is our comparison of the Fusion 360 animation that we used in our championships. And then the video on the right is going to be the new Blender robot animation that I did. And you can see that it was really choppy at some points. That was probably a mistake on my part on how I messed up the animating. But when you look at the Blender robot animation, you'll be able to see, even despite that little hiccup, that the Blender robot animation is going to be a lot cleaner and smoother looking. So you could see that with the renderings of the textures, it looked a lot more realistic and a lot cleaner, I guess. And it was just a much better way to present a robot than in the Fusion 360 version. So now to the second part of this presentation, how to create a bill of materials in Fusion 360. So because of COVID-19, everyone has to work at home, so teams can't meet up together. So it's important to create bill of materials for the hardware team so that the coach knows what to buy from the store. So when you're planning a robot, you can send the bill of materials to your coach, and then they can get you whatever you need. So what is a BOM? As I said, it's a bill of materials, and it's just a list of the materials that make up a product or an assembly that you have made. And it lays out all the information to create a product. So this image of a short bill of materials is actually from our BOM last year. And I just took that to give an example. So the first thing to do when you create a BOM in Fusion 360 is to make a 2D drawing of whatever model you want to make a BOM of. So to create that 2D drawing, you would right-click on it and hit New Drawing from Design. And from that, it should give you a page that looks sort of like this. And as you can see with this image, this is just a base image of the model that I created a 2D drawing of. And you can see that it's really small, and it's kind of hard to see the entire model because of the orientation. So to fix that, we can scale the image and then also change the orientation. So this is the first view that I had, where the orientation was from the front and the scale was 1:8. So I changed it to southeast isometric so we could get a better view of it. and I also scaled it to 1 to 4 so that the image could be larger. Now, to create the actual bomb, you can create a table, and that's just under table, and there's a table button. And by default, it should say select drawing view, and that's what you want it to say. And then from there, it should automatically create this table with the part number of whatever your part is called, the material, which you can change, and the quantity of how many are in that model. But as I said, there's a part number. Usually, people rename the part name, or when you create a custom part, it's automatically called component, and then a random number. So, but you don't want that. You want it to have the actual name, so your coach or your team can identify and see that part name and automatically know what that part is. So to change that, you would go into the assembly or the model file you have, right-click on the parts called component, go to properties, and change the part number. Now, usually you would change the part name, but changing the part name only changes that in the actual file. But when you create a bill of materials in Fusion 360, if you change the part name, it won't show up on the bill of materials. So you would actually have to change the part number instead.
And what's Patrick presenting? Oh.
I don't know. What is Patrick presenting?
I'm sorry.
Oh, okay. Oh, I thought you were asking. Wait, were you asking me that? Okay.
No, my wife's in the other room at the beginner's session, and I'm looking at it on the laptop. I was just asking her. I didn't realize I was not on mute. I'm sorry about that.
Oh, that's okay. I'm almost done. I think this is the last page. So the last thing that you have to do with a bomb is to export it. Of course, you could just take a snapshot of it, but it's better if you just export it as it is. So there are 4 ways to export it: as a PDF, a DWG, DXF, or a CSV file. Personally, I would say a PDF or a CSV file would be better. This is the PDF format, and this is the CSV file format. With the PDF, you can see the actual model. You can see the bomb, the name, like just all the specifics. And in the bomb, it also points to the part of the part to where it is. So for example, the beam bearing cover is item number 1, and then item 1 just points to it. And then the second part is a ref part, and there's a number 2 pointing at it. And then this CSV file or spreadsheet, it just shows the basic stuff of the part number, how many it has, and just the number it is. But it doesn't show the image, but they usually don't anyway, so that's fine. And then these are just 2 websites that I use to get information for Blender. I used a couple photos, and I took some ways to explain how to use it. So if you want, you can just save these 2 websites if you want, if you're interested in Blender. Yeah, that's all from my presentation. Yeah. If you have any questions, then feel free to ask.
Okay, any questions for Max can go into the Zoom chat, We're now going to move on to our final drawing before we end the workshop. So let me share my screen. Okay, so this giveaway is going to be for the GoBuilda 5202 motors, and it's going to be a set of 4. So we'll go to here. I try to get down everybody's name that you guys put next to your Zoom names. Okay, so someone from team 11419, if you could send me a private chat or something to claim your prize. Okay, so I think it's Arav, sorry if I mispronounced that, and Preston. You guys both sent me private chats. One of you guys just send me either like a contact email or a contact phone number for your team so that we can get back to you after this workshop's over for more details on the giveaway. Okay. So that is it for our workshop today. You can leave this session directly if you want, or you can return to our main session, the webinar, if you do want to stay and find out the winners of our used monitor survey. But that is it for today. So thank you for joining. I hope you learned something new.